Okay, so we have not had an existence and uniqueness theorem in a while, so let me give you one. Existence and uniqueness for constant coefficient, second order linear differential equations. What word am I missing right now? And why is that exciting?
Homogeneous,
Oh.
non-homogeneous.
Yeah, I'm missing the homogeneous or non-homogeneous specifier, right?
Okay.
This is true regardless. So I'm going to write down a non-homogeneous one, and you could assume that the homogeneous solution also works. So let me call my differential equation y double prime plus p of x y prime plus q of x y equals, oh, I'm writing p's and q's, which means that I miswrote my, what did I miswrite?
It's not constant coefficient.
It's not even required to be constant coefficient.
Okay.
Constant coefficient would satisfy this, right?
Sure.
You guys see that? Also, homogeneous would satisfy this. You guys with me? Okay. Let's see. So to this, I need to add if P and Q and F are continuous on an interval, say from A to B. With some point in A to B, then I have my second order differential equation and also some initial conditions. So say y of x naught is k naught and y prime at x naught is k1. For this thing, right, like this kind of object, one should think, yeah, this is an initial value problem, right? So when you see a second order thing, what's your real world application for second order differential equations? Springs. Okay, so you want to think spring at this thing. Is that totally honest?
Maybe not all. Probably
No.
not.
Please note in here I apparently have a variable friction and also variable spring constant and external forcing. Right?
So the material of the spring is changing as it's bouncing, and also the.
Okay, careful. There is a reasonable interpretation for the spring constant changing, which is that the spring is made out of metal that gets more ductile as it gets heated.
Yeah.
Right? And it's getting heated because the friction is absorbing some energy, right? And the friction might change as your object kind of polishes whatever it's bouncing back and forth on.
Or the material it's on changes.
You guys see that?
Have a non-hooking spring.
Or you have a non-hook spring.
Hooke's law is not like a universal law for all springs. There are a lot of springs that fit that description. So there's some that don't.
Yeah, I don't know what you would do if you had a non-hook spring here. You could maybe come up with a Hooke's law approximation for it. But I built the idea of second order differential equations applying to springs. I built that out of Hooke's law. Right?
Well, wait a minute. All right.
When
For
I-
Hooke's law, wouldn't you just have to set P of x equal to itself constant?
Yeah. So if I had a spring with constant coefficient, that would be setting Q constant. And if I had some constant friction in the system, that would be setting P constant. And then some external force would be applying this F, right? You guys all good with that? So I'm thinking spring at this thing with an initial displacement and an initial velocity. You guys cool with that? So spring with initial displacement, initial velocity. Okay? Now, cool thing has unique solution on AB. Please note, the cool thing about this one, this existence and uniqueness theorem is stronger than the other one we got. You guys remember the first time I gave you an existence and uniqueness theorem, you were like, well, you can solve it on some subinterval as long as everything's sufficiently nice. On this one, I'm telling you it has a solution everywhere that P, Q, and F are continuous. You guys pull that? Which is nice. We can also actually do a little better than this. When we have Laplace transforms, we can get a little further, and we can make some assumptions about F being non-continuous and still get away with this thing. Cool? Like, we can whack a spring with a hammer and still get a solution out of it. That's unique. Cool? All right, so this is existence and uniqueness for springs. Now I think I probably need to, oh yeah, I need to solve non-homogeneous things before this means much, right? You guys with me? Okay, so